I'm Richard Hollingham. Welcome to the Planet Earth podcast. And this time I'm in Leicester to discover how air quality is being monitored during the 2012 Olympics. Also, how small is a dwarf elephant and how big is your water footprint?
The average for a T-shirt would be in the order of about 1,500 litres of water to produce that single garment.
The World Health Organization estimates that every year almost 2.5 million people worldwide die as a direct result of air pollution. Many more suffer respiratory problems and lung disease, which can cut life expectancy by years. In London, for instance, air quality regularly fails to meet European standards. Well, here at the University of Leicester, scientists and engineers have been developing a new scanner system to monitor urban air pollution, which they're getting ready to deploy in time for the Olympic Games. And with me outside the laboratory here, with appropriately enough a football match going on in the background, Roland Lee and Rosie Graves from the university's Earth Observation Science Group. Now, Roland, just give us a sense of what's in the air around us. We're in a semi-urban location here.
So our urban environments are cleaner than they used to be, but still we have a lot of emissions that come from the traffic network in particular. We have nitrogen dioxide, we have particulate matter, and we have ozone coming out of the exhaust of cars that then we breathe in.
And what's that doing to us?
Some of it affects the airways to the lungs, so what we breathe in and our respiratory tract and the way that our body responds to that. And some of it gets into our bloodstream and actually affects the cardiovascular system and how our heart responds.
So none of that's good. Where's it all coming from?
Much of it, 95% of the nitrogen dioxide, for example, in an urban environment, comes from the vehicles, from cars, from heavy goods vehicles, and from buses.
Now, pollution is already monitored. There are monitoring stations around the country, particularly in big cities. But you've developed a new type of scanner, which is here in front of us. Now, I guess it looks a bit like an oversized speed camera. Or, if you're into your television history, one of the original BBC TV cameras from the 1930s, mounted on a plinth. So that means it can rotate. It's triangular, I suppose, with a hatch at one side.
We realised several years ago that we could monitor air quality using scattered sunlight. So there is a possibility to create an instrument that just receives scattered sunlight and tells you how much nitrogen dioxide there is in the air. So this instrument is designed to sit on top of a tall building and produce an image of the nitrogen dioxide over a complete urban environment, really letting you see the individual emission sources and where those pollutants end up downwind.
So does that mean you can map where these particular pollutants are, where these chemicals are in the atmosphere, rather than get a snapshot of how much there is?
Exactly, yes. Yes, with multiple instruments you can get a 3D reconstruction of where these gas fields are. So traditional sensors take in a single point measurement. They suck in air down a tube and they give you a very accurate point measurement that might be by a roadside. We, between 2 or 3 instruments, can map out a complete urban area and tell you where the nitrogen dioxide is in that space.
It is a curious-looking machine. It's, imagine around the size of a microwave oven, but a triangular microwave oven. And you look inside, it's full of circuit boards and wires. And there's a box in the middle which is covered in a silver bubble wrap. I guess that's the heart of it.
Exactly, that's the heart of the instrument. That's a spectrometer that was originally designed to be a satellite instrument for air quality mapping by Surrey Satellite Technologies. We built the first one of these spectrometers ever to be made in the world. It produces very, very nice data for exactly what we're needing here, which is air quality information in our scattered sunlight data. So we have one of those spectrometers sat in the middle of a rotating turret, collecting sunlight and mapping out the air quality.
And when you say a spectrometer, what is that actually measuring?
So the spectrometer takes in sunlight. In our case, we have filters that means it's just above UV to what is about yellow to red. And we then pull out bits of information in the blue to green bits of that light to the point where it's much more sensitive than the human eye would be to those slight subtle changes in colour. But this spectrometer can really tell us how much of a one shade of green there is, and that one shade of green is a shade that is absorbed by nitrogen dioxide. So with that real high sensitivity to these colours, you can pull out that information on the gases.
Now, Rosie, you're looking to use this during the Olympics, really as a way of testing it out.
Yeah, so as part of a UK-wide project called ClearFlow, we'll be going to the Olympics in July and August this year. We'll be deploying 3 of the instruments on 3 different buildings around the city centre to the west of the city generally, and trying to map out the pollution over the city in this quite unusual time for us. Obviously the roads will be different, there'll be a lot more people in London to normal, so it'll be quite interesting to see what happens.
So is that why you're doing it at the Olympics, when you've got this very different traffic flows and a huge number of people as well in the city?
Yeah, so it's important to know what the conditions were like during the Olympics and see how we coped with this extra traffic and things. And we also did a field campaign in January and February this year in London to see how it was before the Olympics. So then we'll be looking at what happens during the Olympics and trying to compare the two.
So, Roland, how is information from this going to be used, or from other sensors going to be used? Because you can look right now on a website and see London or a lot of other cities around the country and around the world that pollution levels are being exceeded. This will, again, tell you that pollution levels are being exceeded.
What this instrument can do is it can map the emission source and where that emission goes downwind. Much of the information we have at the moment is from these point sources, which then are put into a model, and that model then produces a good figure that tells you what is happening over an urban environment over a year, or over a month, or over a week. What this instrument can do is it can say, we've imaged this being emitted at point source, we've watched it go downwind, we've watched it mix, we've watched it dynamically evolve, chemically evolve, and then we've seen where it ends up. And that can happen for every single emission source, even emission sources you didn't realise were there before. So, for example, here, several years ago, we picked up the railway station in Leicester with an early prototype of this instrument and watched trains leave the railway station. And that was quite a new bit of information for our local authority that didn't really realise how much was coming out of an individual train as it pulled out of the station and where that emission went.
Because they are quite smelly old diesel trains that go through Leicester, aren't they?
They certainly can be.
And do you think things like this will ultimately make a difference and bring down, for instance, those alarming number of deaths from urban air pollution?
We are, in fact, developing systems which take in data from this and enable the local authorities to make decisions on traffic management and air quality management at the same time. And that's where we're really trying to make a difference, where people can be informed when there's going to be poor air quality days in the future, so the local authority knows where to direct traffic, which roads to avoid, which areas have sensitised individuals. That's really where you start making a difference to people's lives and having that societal impact that we all try and achieve.
Roland Lee and Rosie Graves, thank you both very much. This is the Planet Earth podcast from the University of Leicester. And as you'd expect, we'll be putting some pictures of CityScan on our Facebook page. You can also follow us on Twitter, and do visit Planet Earth Online for news and features about the natural world. There's an awful lot that scientists can learn about the past from fossils, but one particular extinct species is proving a tough nut to crack. Dwarf elephants last roamed the Earth more than 10,000 years ago. About a metre tall, fully grown, they are even considered by some to be responsible for the legend of the one-eyed Cyclops. But although they've been studied for 150 years, fundamental information about dwarf elephants is still missing, and no one's exactly sure how the different species evolved. Paleontologist Victoria Herridge from London's Natural History Museum is part of an international project trying to solve the mystery. Victoria studies dwarf elephant fossils found on a number of Mediterranean islands. Sue Nelson went to meet her in one of the museum's basement stores.
In here we have a whole drawer full of dwarf elephant teeth from Cyprus, and they're all different sizes, but most of them are smaller than the size of my hand, which sounds quite big for a tooth, but for an elephant tooth that's absolutely tiny. So if you were to look at an elephant tooth, what you see usually is a series of ridges in sequence, one after the other. We call each of those ridges a plate, and an elephant tooth is made up of several of those. They have 6 teeth through their life, and as the elephant grows bigger, the teeth grow bigger. So the smaller teeth are actually the teeth of younger elephants. And so these are elephants that would have died before they were fully adult. And I've got one in this other hand here, which is about golf ball size, and that would probably be, if it was equivalent to an African elephant, it would be about, say, 4 or 5 years old.
You've been studying these dwarf elephant fossils from Mediterranean islands. Are they particularly common on islands then?
You only find dwarf elephants on islands. It seems to be an island phenomena. It's not just dwarf elephants you get. You also get on Cyprus, dwarf hippopotamus, and similarly on Sicily you get dwarf hippopotamus, dwarf deer, dwarf elephants, and also on Crete you get dwarf hippopotamus, dwarf elephants and dwarf deer. It seems that on islands, when big animals become isolated there, they tend to evolve to become smaller, and conversely, the small animals like mice and rats tend to evolve to become larger, which is an interesting phenomenon we call the island rule.
As this project wants to look at the different environmental changes and the effect that had on the species, I assume then that means that you suspect that the change in climate had something to do with their evolution, why they became the size they did, and perhaps why they became extinct as well.
Yes, certainly a possibility. If you look at modern day islands, we know that the number of species that live on an island is related to how big the island is and also how difficult it is to get to that island from the mainland. So because there's a relationship between island area and distance from the mainland, it seems sensible to assume that islands in particular and the animals that live on them might be affected by sea level change. So if the sea level was to rise, as we fear it might do in the next few years, you would effectively see a greater impact of that on islands, because you would get a smaller island which might affect the number of species that can live there, and it will also affect how far that island is from the mainland, because of course the sea has risen. So although the land hasn't moved, it's become harder to get between the two. So using that as a starting point, we then thought, well, the period that we're interested in, which is called the Quaternary, so the last 2.5–3 million years, a lot of that was characterised by these shifts between ice ages and warm stages, and that will then be followed by a rise in sea level. So we think, for instance, at the peak of the last ice age, the sea level was 120 metres or so lower than it is now.
Wow.
Yeah, so quite an extreme difference. But because it's happened several times, so about every 100,000 years, what you've got there is a repeated example of this situation changing. So we aren't looking at the effects of the climate per se, it's more the associated impact of that climate change, i.e. sea level change, that may affect the environment in which animals find themselves. Now, Sicily is very, very close to mainland Italy. If you stand on the coast at Messina, which is a town on the northeast corner of Sicily, you can actually see on a clear day the Italian mainland, so very, very close. But the sea that separates the two is about 100 metres or so deep, and so 120 metres of sea level drop would join Sicily to the mainland. It would also, interestingly, join Malta to Sicily. And so at low sea level, what you might get is, if you like, the mainland kind of reaching out and encompassing Sicily and Malta, and that would become part of the mainland. Now, when the climate shifted again, and you got a change from, say, an ice age back to a warm stage, then, of course, sea level would rise, and you'd find yourself with two islands, Sicily and Malta, and the animals that were there, that had effectively been mainland animals until that sea level change, now become isolated on these islands. And it's following that isolation that the evolution towards becoming smaller, we think, happened. So we're wondering whether or not you can effectively associate some of these species with some of those climatic-driven sea level changes of the past. What I also want to show you here is a similar sized tooth, slightly larger, but in more or less the same size bracket, which is from Malta. And so what you can see here is two elephant teeth, roughly the same size, and that tells us that on these two separate islands there were two species of dwarf elephant that were roughly the same size. Now, we think both of these species had the same ancestor, which is known as the straight-tusked elephant, Paleoloxodon antiquus, which is an elephant species that was found all over Europe from about 800,000 years ago to about 30,000 years ago. And you can see, if I just lift up this very heavy tooth here.
Yeah, you need two hands.
Yeah, two hands. This is not going to fit in one hand. This is, you can hear how heavy it is from the clunk there.
Yes, that's bigger than a shoebox.
But this is a straight-tusked elephant tooth from Clacton-on-Sea in Essex. So we had straight-tusked elephants in the UK, but that species actually stretched all the way across Europe down to the far south, so into Greece, into Italy, which makes sense because we think that was probably the ancestral species of these dwarf elephants that somehow reached these islands, perhaps at low sea level, when the sea levels were different in the past, and then became isolated on those islands when the sea level rose again. And when it was isolated there, it evolved from being very, very large, so a straight-tusked elephant would have been about 4 metres tall, much taller than the African elephant, which comes in about just over 3 metres, would have weighed about 10 tonnes. Contrast that again with the African elephant, the largest living land mammal, was about 7 tonnes. So we're talking about a big elephant species here. And that it would have evolved on those islands to something as tiny as this 1 metre tall species. And that's a very extreme example of evolutionary change. And it's a wonderful example because it obviously happened again and again on different islands. So it happened on Cyprus, it happened on Malta, it happened on Sicily, it happened on Crete. And because it happened so many times, it starts to give us, if you like, a natural experiment. These islands are kind of like a natural laboratory for evolution in real space and time, and it's a really neat potential way of getting a handle on how quickly evolution happens and potentially how and why it happens. And that's why studying these elephant species potentially will give us greater insight into much broader evolutionary and biological trends.
Victoria Herridge talking to Sue Nelson at the Natural History Museum in London. Now, we're all used to being told to reduce our carbon footprints, but what about our water footprints? A water footprint covers the amount of water involved in providing a product or service, and almost everything has a water footprint, from the clothes you wear to the food you eat. It turns out that even a glass of water has a water footprint. I've been talking to Martin Tillotson from Water at Leeds, based at Leeds University, who's developing ways of measuring and reducing water footprints. I started by asking him how much water had gone into my shirt.
The average for a T-shirt would be in the order of about 1,500 litres of water to produce that single garment.
So a T-shirt, 1,500 litres per T-shirt in the production, and then you've got all the washing and all the rest of it. So you're talking over a lifetime, thousands of litres.
Indeed you are, yeah. That's one of the reasons why we're interested in this type of work, because what it does is it gives you a much more accurate indication of the amount of water that as an individual or that as a business or, you know, even as a region or a nation you are actually consuming.
OK, here's an easy one. I've got a cup in front of me of black coffee. So a black Americano. A quick slurp of that. How much water is associated with that? Presumably just the water that's in the cup there.
Not at all. And even the water that has gone into producing that beverage there, so the actual volume of water in that cup will have a water footprint that is significantly larger than the volume of water that's contained in there. So, for example, that water will have been sourced, presumably somewhere in Yorkshire. It will have gone through a treatment process. That treatment process will have involved the use of chemicals, the use of energy. It will have gone through pipes that would have required the use of energy. And all of those separate steps have a water footprint associated with them.
So even water has a water footprint?
Even water has a water footprint, yeah. And one of the things that we're interested in doing here at Leeds is helping the water industry to understand what its actual water footprint is.
Now, these are staggering numbers you're talking about, but why is this important? Why does this matter?
In a world in which resources are increasingly being recognised as being finite. So you look at energy, for example, and we know that fossil fuels have a finite life associated with them. We also know that renewable energy, for example, has a significant water footprint associated with it. We also know that there's going to be increased competition in the future for land availability, for example, for people to live on, for the production of raw materials, for the production of biofuels, and that type of thing. So all of those things need to be balanced. We have quite significant targets imposed around reducing carbon emissions, but we don't hear quite so much about water at the moment. I think that's starting to change.
And so who does this? If I buy this coffee, small black Americano, which claims to be fair trade on the side, and yet uses 140 litres of water, should I feel bad about that?
Well, it largely depends upon the environment in which the water is taken from to actually make that cup of coffee. So, for example, if that coffee is being sourced in a part of the world that is already under water stress and where perhaps other water concerns, the local population, are suffering from water shortages, then perhaps that is a reason to feel a little bit guilty about it. On the other hand, there are obviously the economic benefits, particularly with fair trade brands that are derived from you buying coffee from those sorts of sources. So having a knowledge of water footprint at the consumer level will help you to make informed choices about the sorts of products and the sorts of services that you might want to buy.
So really everything we buy, everything we consume has a water footprint associated with it. So really there should be on this sweatshirt, as well as a label saying 90% cotton, there should be a label saying what its water footprint is, and it would be pretty big.
Well, yeah, I mean, there are similar labels that are available, for example, for carbon footprinting. And it has been talked about, a similar sort of labelling scheme for the amount of water that, goes into different products. I think the difficulty with those sorts of schemes is that they can be confusing to the consumer. And so perhaps, one of the things that I would like to see would be an overall scheme, if you like, that says that, this company or this product has been made in a sustainable way, one of which is making the maximum efficiency and optimising the use of the overall resource input as far as possible.
Martin Tillotson from the University of Leeds. Now, we did have lunch together after that interview, both trying to choose, as we went round the counters, the meal with the lowest water footprint. Although I did have a coffee afterwards. And that's the Planet Earth podcast from the Natural Environment Research Council. I'm Richard Hollingham. Thanks for listening.